All right, so let's take a look at this we did in class talking about a function. So let's start off thinking about this. So Jessica recently visited an amusement park with her family. To get into the park, a visitor must pay $10. Once inside, each ride costs $2. The amount of money spent can be modeled by the equation, where, and I think this should say x equals money spent and y equals rides taken. Okay? So if we go into the park and take no rides, then we pay $10, right? So let's maybe count by twos. 10 would be right there. So that's where our first point would be, right? So then if we ride one ride, that would be $12. So if I go one ride, right, bump me up to 12. 2 rides would be 14. 3 rides, 16, 4, 18, and so on, right, until we get to 5 and 20. All right? So this is what we call a function. Okay? Now with a function, there's 3 rules to be a function. Okay? So there has to be 2 groups. We have rides taken connected with money spent. Okay, there has to be a pattern. For every ride, we're adding 2. And then a special requirement. Okay? And that special requirement is what we're going to talk about a little more. Okay? So again, those 2 groups, we often call them the input with the output, the x value with the y value, the independent variable with the dependent variable, and the domain with the range. Okay? So the pattern, there's a lot of different ways that we have some patterns, but the special requirement, and this is really what we focus on when we call something a function. Okay? So a few different ways to talk about it. So you can say for every input, there corresponds exactly one output. Okay? For each x, there's only one y. There's no 2 pairs with the same x and different y. Okay? For all the ordered pairs, so all these solutions here, okay, that from the domain is only paired with one type of range or y. Okay? But let's talk about what that means, and we've got a good example to look about that. Okay? Let's think about a candy machine, and we got some Venn diagrams kind of helping us represent this. So if you got a candy machine, right, you've got the place to put money in, and then you've got a keypad, right? And then you type in what you want, and it falls down and comes to you, right? So that kind of candy machine. So let's say you go up there and you pay and you want a Kit Kat, and you type in C4, and C4 will say is right over here, okay? And it's got the Kit Kat in there, but instead a Snickers drops out from a different one, okay? So if that happens, we're pretty upset, right? Because that's not reliable. Okay, functions are reliable. So when we have an input, okay, if there's 2 possibilities, like our candy machine where we typed something in and there was 2 possibilities, sometimes it would be Kit Kat, sometimes it would be a Snickers, okay, that's not a function. It's not reliable. It's not fulfilling that special requirement. Okay, all the rest is, but it's not that special requirement. Okay? Something that would be functioning properly or looking like a function would be like this one. We typed in B2, boom, always spits out a Snickers. If we type in C4, always get a Kit Kat. D6, always get a Twix. Okay, that's a situation that is a function, because for each one of these inputs here, I only ever get one output. It's reliable. I know exactly what I'm getting. Okay, so like it says here, each input corresponds exactly to one output. Okay. Depending on which button we push, okay, that tells us what candy we get. So the output, the candy, would be the dependent variable, and what we push would be the independent variable. Okay, let's take a look at a third situation. So if we look at this one, okay, you can see if I press E3, I get a Twix. A4, get a Twix. D6, get a Twix. So this is like candy machine just full of Twixes, huh? Okay, so if we look at this one, we say, hey, this went to 2 different ones, and that didn't work. That wasn't a function. This one was because they all went separately. However, this one actually is a function too. It's a function because every time I hit A3, I get Twix. Every time I hit A4, Twix. I don't get something different. So it's all right for us to have a similar output with a different input because it's still reliable. I know every time E3 is pressed, I get a Twix. Here, I don't know what I'm getting. That's why it doesn't work. This one, know exactly what I'm getting. This one, I don't. So the idea here is, let's take a look at a few examples. So if we're given a table, what I'm looking at to see if it's a function or not is my x variables, okay? And I see that they all have different numbers. That's good. Then I check to see what each one is paired up with. Are any of those the same number giving me a different response? No. So look at C. I've got a 0 and a 0. Okay, so if I give you a 0, there's a 3 or 4 possibility. Here I give you 0, I'm always getting 3 back. I give you 3, I get 12 back. Okay, here I'm giving you a 1, I get a 2 back. Okay, so yes, this is a function. Yes, a function. This one, if I give you a 0, you've got the option. You can give me a 3 or a 4. That's not reliable, so no, not a function. Okay, same with D. If I give you a -1, you can give me a 3 or a 5. Right there, that tells me it's not a function. However, if I give you a 3, you give me back an 8, 7, an 8, 15, an 8. That is a function. Okay? If we look at sets of points, 5 gives me 10, 6, 11, 7, 13, 8, 16. Okay? No matter which input I give you, that first variable right in the coordinate, you have to give me a certain one back. That's a function. Oops, and I meant to write that in orange. Okay, however, look at G. -10 could be 1, -10 could be 2, -10 could be 3, or -10 could be 4. Okay, that one is not a function. Okay, because it's got the same input giving me different outputs. All right, H, the amount of money spent at a movie theater versus the number of tickets purchased. So you have to decide what's my independent and what's my dependent, okay, for these two. So the amount of money spent at a movie theater would probably be the dependent, depending on the number of tickets. Okay, so could I buy the same amount of tickets and have a different amount of money spent? Okay, well, it would depend on the tickets, right? If I have children as opposed to adults, or okay, or I go with deluxe, a 3D show as opposed to that. So I would say no, that's not a function because there are multiple ways that I could get the same amount of tickets. Now, if you were saying the same exact type of tickets, then yeah, it would be a function. Okay, I, the age of someone versus their height. Okay, so the age would be the independent, their height would be dependent. Can I give you an age and have different heights? Yeah, definitely I can. So that one would also be a no. Okay, what about a graph? Okay, there's a great way that you can do this called the vertical line test. Okay, and the idea with the vertical line test is that you're able to take a vertical line and you pass it across and see if the graph touches that vertical line more than once. Okay, so I got myself a vertical line here. Okay, so what I do is I pass it across, and notice it's pointing at two places, okay? Right here and right here when x equals 4. So the idea here is if I were making a table, if I gave you a 4, I would have a y value of 4 or a y value of -4 in response, okay? That's why it works, is because it's giving you that straight line represents the x input. And if it touches more than once, that represents having multiple outputs. Okay, so this one would definitely be a no. Okay, let me see if I can get it again. There we go. Oh, hold on. Sometimes it's hard to grab. Oh my goodness. Having a lot of trouble here. Alright, finally got it. So let's do this one. So it only touches one point at a time, doesn't it? Oh, right there at K, 2 at the same time, so that would be a no. Look at M. down at the bottom. Going through that only touches once. Look at J up at the top. Only touches once. So, yes, a function, yes, a function, no, not a function, because it touches those two. Okay? So then number 3, come up with some examples of your own of relationships that are functions. Okay? I'll leave that up to you guys to do that one. And then 2 that aren't functions. Okay? Remember, look at the x's, the inputs. For every input, you only ever can have one possible output. Okay? Whereas if it's not a function, for your input, you would want to have at least 2, if not more, different outputs. That's what you're looking for. Okay, so we talked a little bit about the dependent variable and the independent variable, but understanding those can help us determine if it's a function or not. Okay? So what we want to do is label what the independent variable and a dependent. So remember, the independent is the one that you can change, and it doesn't matter how you change it, but it'll affect the other one. So the size of your family versus the cost of groceries. Okay? So I would say this one, the size of your family, would be independent, and depending on how big the size is, that would determine how many groceries you're getting in there for the cost. Okay, the age of your car versus the value of your car. Okay, as your car gets older, that determines its value. So that's how that would stack up. The speed of a sprinter versus the time it takes to run a race. Okay, your speed, you can change that, faster or slower. That's going to determine how long it takes you to run the race. The distance you can drive versus the amount of gas in the tank. Okay, this one, generally, you put the gas in, and that determines, based on your car, how far you can get. You put less gas in, you go less. Okay? All right, now function notation. Okay, so we said that first problem, x was the money spent, y was the rides taken. Okay, since money spent is a function of the number of rides taken, we can replace the y with the f of x. Okay, and that's how we read it, f of x. So now f of x becomes the money spent, and x, oops, sorry, backwards. Did I mix them up? I did, didn't I? That should be x, that should be y, huh? There we go. Sorry, did I mess that up at the beginning too? I did, didn't I? That was silly of me. I apologize. There we go. All better now. Okay, so we replace that y with f of x. Okay, we like that because that f just basically tells us it's a function right off the bat. So we don't even have to guess. We know exactly what it is. Okay. So if we think about going back to this problem, if we made an equation here, right, it would have been y equals 2x plus 10, or 10 plus 2x. Okay. So same thing here. Instead of y, we go f of x equals 10 plus 2x. Okay? And again, that just tells us it's a function. We don't have to guess if it's a function or not. That f tells me it's a function, and the variable we're using is the x. Okay? So what's in here is the input, and you see it in the relationship, the pattern here. Okay? And that f of x stands for the output. If you remember, we were dealing with a sub n. Okay? F of x is the same exact thing. Okay, so we've got our equation, 10 plus 2x. Okay, f of x was this, and x was rides taken. Okay, now what if we want to calculate the amount if we go on 3 rides? So we can evaluate a function. Okay, this is really annoying that let's not pay attention to that. Okay, so if I've got f of x equals 10 plus 2x, I want to find, it says 3 rides, so I want to find where 3 of what rides are. So 3 becomes my input when you evaluate a function, and then in my function, wherever there was an x, it becomes 3. And it's 2 times x, so it's 2 times 3. So to evaluate, I don't need to touch this anymore, and I just go 10 plus 2 times 3, which is 6. 10 plus 6 is 16. So f of 3 equals 16. What that means is, on that table, or that point, that 3 and 16 are connected together. Okay? And so we take that independent variable x and find the dependent f of x. Okay? And we just have to evaluate the one side. It's not like when we were solving for a variable and getting it by itself. This time we're evaluating because we know exactly what we want to find and how to get there. Okay? So, these last ones. Identify the dependent variable independent, write a function using function notation, and find f of 3 to tell what it means in the context of the situation. So f of 3 being the input. Okay, so number 6. The initial fee for placing a color ad in a newspaper is $20. Each line of the ad costs an additional $7. Cost versus number of lines. Okay, so the lines are what we change. That's independent. The cost is dependent. Okay, so I'm going to go f of x, my cost, equals, okay, because cost would be f of x, equals, well, we have to pay $20. Then for each additional line, we're adding 7 times x. X would be the lines. So we want to know now, what if we add 3 lines to it? So to solve that, I go f of 3 equals 20 plus 7 times 3. Okay, so f of 3 equals 20 plus 21. 20 plus 21 is 41. So f of 3 equals 41. So that tells me is if I have 3 lines, it's going to cost me $41. Okay? Alright. 7. A cheese pizza costs $7. Each additional topping is $2. Cost versus number of toppings. Again, cost is going to be our f of x, our dependent, and our independent is the number of toppings. That's our x. So f of x equals, we start with $7, add $2 for each topping. Now what if we have 3 toppings on it, because that's what this 3 stands for. So I get 7 plus 6, which is 13. So to put 3 toppings on my pizza, it's going to cost me $13. Okay? 8. A person burns 580 calories for each hour they run. Calories burned versus time running. Time running is my independent, that's our x. Calories dependent, that's our f of x. So f of x equals 580 times the hours they run. Now, I could say f of h equals 580 times h if I like using the h instead, but we'll keep using x. Now, f of 3 tells me, what if I run 3 hours? Well, 580 times 3. Okay, so f of 3 equals, so I go 580 times 3, and I get 1,740. So when I run for 3 hours, I burn 1,740 calories. So hopefully this is helping make some sense for you guys. Okay, number 9. You purchase an antique car for $15,000. Each year the value of the car increases by 5%. So the time is my independent. Value of the car is dependent. So I go f of x equals, we started at 15,000, and what am I doing? Now, you got to remember with percents here, okay? So we take 15,000, and we would times it by 0.05. We'd take that, and we'd add it back to 15,000, okay? Well, that 15,000 is like 100%, and we're adding 5% to it, so we're growing by 105%. So if I multiply by 1.05, that will give me the same result to the x power. Okay, so in 3 years, f of 3, how much is it gonna be worth? Well, using my calculator, I go 1.05 to the third, and it gives me 1.157625 times 15,000. So times 15,000, and we should get f of 3 equals 17,364.38 when I round for money. So in 3 years, my car is now worth $17,000. Okay, and number 10. What are other examples of functions we have explored so far this year? Which variable is the independent variable and which is dependent? How can we rewrite these equations using function notation to show the relationship? we've dealt with a lot of these, okay, doing all that sequence stuff. So I'm not going to talk about any of those examples right now, but this should give you a pretty clear idea of what a function is and kind of how we can write them and use them. Okay, there we go, guys.